Tonight, we're going to explore one of the most consequential questions humanity has ever asked itself about its own future. Not the engineering of rockets, not the first footsteps in red dust, but whether the planet we've chosen as our second home will ever actually accept us. Mars sits roughly 142 million miles from the Sun, a desert world about half the diameter of Earth, with a total surface area close to all of Earth's dry land. From a distance, it looks like a smaller cousin, a place we could remake, a backup. But hidden inside that assumption is a problem so fundamental that if it cannot be solved, Mars may never become more than a distant outpost, no matter how advanced our technology gets. The surface pressure on Mars is about 0.6% of Earth's. The air is 95% carbon dioxide and barely 0.1% oxygen. Standing unprotected on Mars is closer to standing at 100,000 feet than to standing on any mountain a human has ever climbed. Consciousness would last about 15 seconds. Life would last about 2 minutes. By the end of tonight, you're going to understand why Mars is not really an engineering problem, how its thin carbon dioxide atmosphere and brutal pressure quietly defeat the dream of a backup planet, and what this means for how we see the fragile, breathable world we already have. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. That planet, smaller than it first appears, sits about 49 million miles farther from the Sun than we do. Think about what that extra distance means. Not just in travel time, not just in communication lag, but in raw warmth. The Sun delivers roughly 43% less energy to Mars than it delivers to Earth. Less heat arriving, less heat staying, and almost none of it held. Mars is roughly half Earth's diameter, about 4,200 miles across compared to our 8,000. That makes it sound manageable, compact, and here is where the numbers pull in two directions at once. Mars has no oceans, no seas. Every square mile of its surface is exposed ground, and because of that, its total surface area comes out almost exactly equal to Earth's total land area. All the continents, all the plains, all the mountain ranges, everything dry on our world, Mars matches it. That sounds like room. It sounds like possibility. But here is where it gets strange. Every single square meter of that matching surface is more hostile than anywhere humans have ever survived without mechanical life support. More hostile than the summit of Everest. More hostile than the floor of the Mariana Trench. More hostile than the interior of Antarctica in winter. Not slightly more hostile. Categorically, fundamentally, lethally more. The surface area is there. The survivability is not. The first reason is cold. Not cold the way we normally use that word. The kind of cold that operates on different terms entirely. On the best day, Mars offers, at the equator, in the middle of summer, in the middle of the afternoon, the temperature can reach about 70 degrees Fahrenheit, 21 degrees Celsius. That is the warmest reading Mars is capable of producing. Stand at that spot, at that moment, and the air temperature near the surface is roughly what you might feel on a pleasant autumn afternoon. Wait, the same location, 12 hours later, drops to about negative 100 degrees Fahrenheit, negative 73 Celsius. In a single day, at the most temperate location on the planet, the temperature swings roughly 170 degrees. Not over seasons, not over weeks, in one rotation. Think about that for a moment. No place on Earth swings anything close to that. The most extreme desert environments on Earth, places like the Sahara or the Atacama, might swing 50 or 60 degrees between day and night. Mars nearly triples that at its most favorable location, and that is the favorable location. The global average surface temperature on Mars is around negative 80 degrees Fahrenheit, negative 62 Celsius. The coldest temperature ever recorded in Antarctica, the coldest place on Earth we have a record for, sits around negative 128 degrees Fahrenheit. Mars does not get that cold in absolute terms, but Antarctica dips to that reading only in rare conditions, at specific locations, at specific times. Mars averages -80 across the entire planet, across the entire year. Water freezes at 32 degrees Fahrenheit. Mars runs about 3 times colder than freezing as a baseline. Not occasionally, not in winter. As the ordinary daily reality of the place, without continuous active heating, any liquid freezes. Any biological system that depends on liquid water, which is every biological system we know of, simply stops. The mechanism behind all of this is the atmosphere. Or rather, the almost complete absence of what an atmosphere is supposed to do. Earth's atmosphere is thick enough and chemically complex enough to act as a thermal blanket. Solar energy arrives during the day, heats the surface, and the atmosphere captures a large portion of that heat and holds it. It does not hold it perfectly. Temperatures still rise and fall, but the transition is buffered, slowed, moderated by the mass of gas surrounding the planet. The atmosphere functions like insulation around a building, slowing the rate at which warmth escapes. Mars has an atmosphere, but it is thin enough that it barely participates in this process at all. The atmospheric pressure at the Martian surface averages about 0.6% of Earth's, which means there is so little gas present that it stores almost no heat. When the sun sets on Mars, there is nothing to hold what the day built. The heat radiates directly from the surface out into space, essentially unimpeded. The temperature collapses, not gradually, not over hours, almost immediately. That is why the swing is so violent. The atmosphere is not a blanket. It is closer to the absence of a blanket, a thin membrane that offers the planet essentially no protection from its own cooling. For a habitat, this creates a problem that never goes away. A structure on Mars cannot simply be well built and left to maintain itself. It requires continuous energy input just to stay above lethal temperatures. The insulation has to be nearly perfect. The power systems have to be reliable without interruption. And every seal, every junction, every window, every airlock becomes a potential failure point. One crack, one failed heater, one power interruption at the wrong moment. The outcome is not discomfort. The outcome is freezing solid, or depending on what else fails, rapid depressurization. The cold and the pressure work together, and they are not forgiving of partial failures. This is the first layer of what Mars is. A surface the size of all Earth's land, with no ocean to moderate it, no thick atmosphere to buffer it, and a daily temperature swing that would kill any unprotected biology in hours. The cold alone, before anything else is considered, demands infrastructure that has no single point of failure. And temperature is only one piece of what the atmosphere fails to provide. That same thinness has a second cost. The atmosphere that cannot hold heat also cannot hold pressure. And pressure for a human body is not a comfort issue. It is a survival threshold. Mars's surface pressure is about 0.6% of Earth's. Earth at sea level sits at roughly 14.7 pounds per square inch. Mars sits at roughly 0.09 pounds per square inch. To put that in terms of altitude, that pressure is roughly equivalent to what you would experience at 100,000 feet above Earth's surface. Well above the altitude where commercial aircraft fly. Well above where weather occurs. Well into what we consider the edge of space. There is a specific altitude on Earth called the Armstrong limit. It sits at around 62,000 feet. Above that altitude, the surrounding pressure drops so low that water boils at human body temperature. Not because of heat, because of the absence of pressure. Liquids require pressure to stay liquid. Remove enough pressure and water vaporizes at 98 degrees Fahrenheit. Mars's entire surface lies well above the Armstrong limit. Every square foot of Mars, every valley, every highland, every equatorial plain at its most temperate. The entire planet, at all times, sits in pressure conditions where unprotected liquid water at body temperature becomes vapor. Here is what that means for an unprotected human body. The moisture on your tongue begins to vaporize. The moisture on the surface of your eyes. The moisture lining your lungs. This is not burning. It is not heat damage. It is the physics of low pressure removing the conditions under which those fluids remain stable. Your circulatory system stays intact because blood is pressurized inside a closed system. Your blood does not boil. But everything exposed, every wet surface in contact with that near vacuum, begins to change state. Consciousness goes in roughly 15 seconds. Not from pain, from oxygen deprivation, because there is essentially no oxygen to breathe. Gases dissolved in body tissues begin to expand. The body swells. Within approximately 2 minutes, the damage is irreversible. This is not speculation. It is grounded in documented accidental decompression incidents from the history of the space program and high-altitude aviation research. The numbers are known. The timeline is confirmed. 15 seconds, 2 minutes. There is no partial version of this. There is no brief exposure that leaves you shaken but recovers. The Armstrong limit is not a threshold where things get difficult. It is a threshold where things stop working entirely. But the answer was stranger than expected, because pressure is only half the problem. Set the pressure aside for a moment. Imagine hypothetically that Mars somehow had Earth-level atmospheric pressure at its surface. Breathable pressure, the kind you feel standing in a field. Would the problem be solved? No. The air itself is wrong. Earth's atmosphere is roughly 78% nitrogen, 21% oxygen, and a trace of argon and other gases. Carbon dioxide makes up about 0.04% of what you breathe on Earth, a small fraction of a fraction, enough to help regulate plant growth and atmospheric chemistry, but essentially absent from what your lungs actually use. Mars's atmosphere is roughly 95% carbon dioxide, 3% nitrogen, about 1.6% argon. Oxygen makes up about 0.13%. That oxygen figure is worth pausing on. Not 21%, not 10%, not even 1%, 0.13%, about 1/60th of what human lungs require. The rest is carbon dioxide. Almost all of it. Breathing Martian air, even at the right pressure, would be roughly equivalent to breathing car exhaust in a near vacuum. The carbon dioxide would overwhelm the respiratory system immediately. The oxygen present is so trace it would register as effectively absent. So Mars fails on two entirely independent axes. The pressure is lethal, the composition is lethal. Remove either problem and the other still kills you. Not one failure. Two, each complete on its own. This is the compound nature of what Mars's atmosphere actually is. It is not a thin version of something breathable. It is not a degraded version of something workable. It is the wrong substance at the wrong density. Both conditions fail independently, and they fail completely. The phrase Mars has an atmosphere is technically accurate. There is gas above the surface. Pressure can be measured. But for the purposes of human survival, calling it an atmosphere is like calling a coat of paint a roof. The word applies. The function does not. And this is the practical consequence that shapes everything about human presence on Mars. Every minute of every day on that surface requires an artificial pressure envelope, a suit, a habitat, a vehicle, something that maintains Earth-like pressure and Earth-like air composition around the human body at all times. There is no stepping outside. There is no cracking a window. There is no moment where the distinction between inside and outside softens. The habitat described earlier, the one that could never have a single failure point because of the cold, also cannot have a single failure point because of the pressure. The same walls that hold heat in also hold atmosphere in. And the consequences of a breach are not gradual. A slow leak in a poorly insulated wall on Earth costs you heating efficiency over weeks. A breach in a Mars habitat begins killing within seconds. Cold and pressure, two separate properties of the same thin atmosphere, both converge on the same engineering demand. No single point of failure, no margin for the unexpected. Continuous active systems, continuous monitoring. A structure that is less like a building and more like a spacecraft that happens to be sitting still. That is what the atmosphere requires before a single human step onto the surface. Before food, before water, before the question of how anyone gets home. The atmosphere alone has already set the terms, and the atmosphere is not finished setting them. And if the air were somehow not trying to kill you, the ground would be. Lower your gaze from that thin, poisonous sky to the surface itself, the regolith, the fine reddish-brown material that covers Mars in every direction, every valley, every plain, every highland. It looks like dirt. It behaves like a threat. The Phoenix lander touched down near the Martian North Pole in 2008 and scooped samples of that surface material to study what was actually in it. What it found was perchlorates, specifically calcium perchlorate, distributed throughout the soil at roughly 0.5% of its total weight. That sounds like a small number. It is not a small problem. Perchlorates are toxic to humans. They interfere with the thyroid gland by blocking the uptake of iodine, the mineral the thyroid depends on to regulate metabolism. Chronic exposure does not kill quickly. It degrades quietly. Hypothyroidism sets in gradually, bringing fatigue, metabolic disruption, difficulty concentrating, a slow erosion of the body's ability to function efficiently. And this is not something a colonist could simply avoid, because the perchlorates are not in a patch of bad soil. They are in all of it. Everywhere Phoenix sampled, everywhere every lander has analyzed, the contamination is present, distributed, and consistent. The agricultural consequence follows directly. You cannot plant crops in raw Martian soil. The perchlorates would accumulate in the plants and move through the food chain into the people eating them. Before any planting, the soil would need to be washed extensively to flush the chemicals out. That washing requires water that is already among the scarcest resources on Mars. And the water used for washing does not disappear clean. It becomes contaminated washer water, which then requires treatment before it can be reused. Every step creates a dependency on the step before it. Every solution costs resources the colony cannot easily afford. But the picture did not hold. The chemical toxicity is not even the property of Martian regolith that would confront colonists most persistently day to day. The dust would. Mars dust is not like ordinary dust. It is finer than talcum powder, with individual particles only a few micrometers across. To give that scale a shape, a human hair is roughly 60 to 70 micrometers wide. Mars dust particles are more than 10 times smaller than that, and they are electrostatically charged. The thin, dry Martian atmosphere creates conditions where particles accumulate static charge easily, causing them to cling aggressively to whatever surface they contact. Suits, visors, seals, joints, sensors, the fine mechanical interfaces that keep a pressurized suit functioning. We have a reference point for what fine, clingy regolith does to crewed missions. The Apollo astronauts who walked on the moon dealt with lunar dust on every outing. Even on missions lasting only a few days, lunar dust got into everything. It scratched helmet visors. It degraded seals. When small amounts came inside the capsule on suits and equipment, astronauts reported breathing problems and irritation. The moon missions lasted days. Some lasted only hours on the surface. A Mars colony would operate in that environment for years, for decades, for lifetimes. And Mars dust carries something lunar dust did not: chemical toxicity. Every time a colonist performs an EVA and returns through the airlock, the suit comes back coated in perchlorates and fine reactive particles. Airlocks can be equipped with vacuums, brushes, and air jets designed to strip contamination from suits before they enter the habitat. The problem is that none of these methods are perfect. Some dust gets through every time, not catastrophically, not visibly. A fine coating, a residue, a thin scattering of particles into the air of a sealed, pressurized habitat. Over days, this is manageable. Over years, it is a permanent low-level inhalation risk. Particles at micrometer scale, once airborne, penetrate deep into the lungs. The long-term health effects of chronic low-level perchlorate dust inhalation on humans are genuinely unknown, because there is no population to study. No one has ever lived in this environment long enough for a pattern to emerge. What we can say with confidence is that no medical researcher would describe these conditions as unlikely to be benign. The body was not designed to breathe this material. It simply was not designed to encounter it at all. So the ground beneath a Mars colonist's feet is not inert. It is not waiting passively. It is chemically reactive, electrostatically clingy, and invasive through every gap and interface that separates inside from outside. And it is everywhere. Not in one region, not at one depth. At the surface, throughout the regolith, distributed across the entire planet. Now lower your gaze further. Past the surface, into what lies below and what has to come from it. Water. A human body needs roughly 2 to 3 litres of water per day just for drinking. Add cooking, basic hygiene, laundry, equipment cleaning, and the number climbs toward 50 litres per person per day at a functioning colony level. On Earth, this is not a logistical problem. Rain falls, rivers flow, groundwater sits in aquifers and refills when it rains. The water cycle, the hydrologic loop of evaporation, clouds, precipitation, and runoff replenishes every source automatically. The planet does the work. Mars does not have a water cycle, not a slow one, not a broken one, not a remnant of one. There is no water cycle at all. Every drop of water that a Mars colony would ever use would need to be extracted from the planet's own frozen reserves, and then kept from being lost. Those reserves exist. Mars has water. But the word has conceals an enormous amount of difficulty. There are 2 main sources. The polar ice caps contain water ice, mixed with frozen carbon dioxide, sitting at temperatures even colder than the Martian average, which is already colder than anywhere on Earth. Extracting water from a polar cap means traveling to an extreme latitude, mining the ice, separating water ice from dry ice, heating the material to release vapor, condensing the vapor back into liquid, and purifying what you collect before anyone drinks it. Every stage requires energy. None of it happens automatically. The second source is ground ice, deposits of frozen water sitting a few centimeters below the regolith surface at latitudes above roughly 30 degrees north and south. Closer to the equator, where colonists would more likely want to build for reasons of temperature and solar power, the ground ice thins and disappears. Get far enough poleward and it reappears, but at the cost of colder conditions and weaker sunlight for power generation. The ice is there. Getting it out and making it usable is a continuous industrial process. This is why recycling becomes not a preference, but a foundation. The International Space Station already operates a water recovery system that captures moisture from the air, processes urine, and returns purified water to the crew. The ISS recovers approximately 93% of its water per cycle. That sounds like nearly perfect, but not perfect matters enormously at scale. A colony of 100 people using 50 litres each per day requires 5,000 litres of water moving through the system daily. At 93% recovery, 7% is lost every cycle. 7% of 5,000 litres is 350 litres per day that must be replaced by fresh extraction from the environment. That is not a one-time startup cost. That is 350 litres every single day, 365 days a year, which comes to roughly 127,000 litres annually. About 127 metric tons of fresh water that must be mined, processed, and introduced into the colony's supply just to maintain basic human needs. That number does not include a single plant, not one hydroponic bay, not one agricultural module. The moment food production begins, water demand multiplies. Water is not a problem the colonists solve at the beginning and then set aside. It is a permanent, energy-bound operational load that runs continuously from the first day to the last. And the ground that holds the water is the same toxic, dusty ground that has been trying to get inside the habitat all along. The 2 problems are not separate. They share the same surface. They share the same source. The deeper you look at Mars, the more clearly you see that the challenges do not arrive one at a time. And even as those losses compound, something larger has been falling on the planet for 1 billion years. The sky above Mars is not simply thin. It is open. There is almost nothing between the surface and the full output of the sun. Nothing between the colonists and the constant stream of charged particles flowing outward through the solar system. On Earth, we take for granted that 2 separate systems stand between us and that radiation. The first is the magnetosphere, a vast invisible shield generated by the churning of molten iron deep inside our planet's core. That churning creates a dynamo, and the dynamo produces a magnetic field that deflects the most energetic particles before they ever reach the upper atmosphere. The second is the atmosphere itself, dense enough to absorb whatever gets through. Both layers working together bring the radiation reaching Earth's surface down to a manageable background level, around 2 to 3 millisieverts per year. A millisievert is a unit of absorbed radiation dose. A chest X-ray delivers about a tenth of a millisievert. A CT scan delivers around 10. For context, radiation workers in most countries are permitted an annual exposure of up to 20 millisieverts before safety regulations require intervention. Earth's natural background sits well below that. We barely notice it. Mars has neither layer. It had one, once. Billions of years ago, when Mars was young and its interior was still hot, the planet generated a magnetic field of its own. Evidence of that ancient field survives in the rocks. Certain regions of the southern hemisphere show faint remnant magnetism, stripes of magnetized crust pressed into the stone like a fingerprint from a planet that no longer exists. But the field is gone. And the reason it is gone connects directly to everything that has been wrong about Mars from the beginning. Mars is smaller. Because it is smaller, it cooled faster. A smaller body loses heat more quickly relative to its volume, and Mars's interior dropped below the threshold needed to sustain a convecting, churning liquid core. The dynamo shut down. The magnetic field collapsed. And once the field was gone, the solar wind, that continuous stream of charged particles flowing outward from the sun, began to work directly on the atmosphere. Over the following billion years, it stripped away most of what Mars had. The planet did not lose its atmosphere in a catastrophe. It lost it slowly, particle by particle, across geologic time, because the shield that would have held it in place was no longer there. Mars's smallness is not incidental to its hostility. It is the source of it. The same property that ended the dynamo ended the atmosphere. The same cooling that silenced the core exposed the surface to everything the sun and the galaxy could deliver. Today, those faint magnetized patches in the southern crust offer no meaningful protection at any global scale. They are relics. The atmosphere, at less than 1% of Earth's thickness, absorbs almost nothing. Radiation reaches the Martian surface nearly unimpeded. The numbers from the surface are not estimates. We have measured them. NASA's Curiosity rover carried a radiation detector, and what it recorded during solar minimum, the quieter part of the sun's activity cycle, was approximately 24 millisieverts per month. That works out to roughly 290 millisieverts per year. Think about what that means in terms of the reference points already established. A radiation worker's annual permitted limit is 20 millisieverts. A colonist on Mars accumulates that dose in roughly 3 weeks, just going about daily life inside a habitat, without a single EVA, without a single unusual event. By the end of the first year, they have absorbed around 15 times the annual limit considered acceptable for the most radiation-exposed workers on Earth. And solar minimum is the baseline. When the sun becomes more active and produces solar particle events, large eruptions of charged particles from the solar surface, the numbers change in hours. A significant solar particle event can deliver several hundred millisieverts in a matter of hours, not over a year, in an afternoon. The health consequences are not theoretical. Chronic exposure at these levels elevates cancer risk. It raises the probability of neurodegenerative disease later in life. It damages both sperm and egg cells. Temporary sterility is possible. Permanent sterility is possible at higher cumulative doses. If reproduction occurs after significant exposure, the risk of genetic mutations passed to children rises, along with increased probability of birth defects. A colony is not simply a collection of individuals making individual risk calculations. It is a population that intends to persist across generations. Radiation at Mars surface levels does not just threaten the first arrivals. It threatens the children born there, and the structure of what a multi-generational community could actually become. But the reality was different. The solution exists. It is not complicated in principle. 3 meters of Martian regolith, roughly 10 feet, piled on top of a habitat brings the radiation dose inside, down toward Earth-like background levels. The physics is straightforward. Regolith is dense enough to absorb the relevant particles. The math works. But the math produces a number that changes the entire engineering picture. Martian regolith has a density of approximately 1.5 grams per cubic centimeter. 3 meters of it stacked on a surface delivers a load of roughly 4,500 kilograms per square meter. That is approximately 9,000 pounds pressing down on every square foot of roof. For a modest habitat with 100 square meters of floor space, roughly the size of a modest apartment, the regolith on the roof alone would weigh approximately 450,000 kilograms, close to 500 tons. And that is just the ceiling. The walls need shielding too. 500 tons of loose dirt does not sit gently on a structure. That structure must bear the weight without collapsing. It must simultaneously hold internal pressure against the near vacuum outside. It must remain airtight through the thermal stress of Martian day-night cycles. It must stay thermally insulated. Every one of those requirements is independently demanding. All of them together in a surface environment with limited equipment, no established fuel infrastructure, and a small crew in pressurized suits doing every task by hand, represent an engineering challenge that is not solved by listing the solution in a design document. Moving 500 tons of material on Mars is not like moving 500 tons on Earth. There are no construction cranes shipped in advance. There is no diesel equipment waiting in a depot. Every piece of heavy machinery that reaches Mars arrives at enormous cost and must itself be maintained, fueled, and operated by people who have no margin for error. What takes weeks on a standard Earth construction site could take months or years on Mars, with a crew fraction of the size, managing fatigue, perchlorate contamination, suit wear, and every other compounding pressure already described. The underground alternative exists in the literature. Mars has lava tubes, long hollow channels formed when ancient volcanic flows hardened on the outside while still molten rock drained from beneath. Some of them are large enough to shelter substantial structures. Caves and subsurface chambers would provide natural radiation shielding without requiring any regolith to be moved at all. But excavation introduces its own problems. Drilling and boring in perchlorate-laced regolith generates dust. That dust is exactly what the colony is already fighting to keep outside. Underground spaces trap contaminated air. They create new vectors for the same chemical hazard the surface presents. In an enclosed environment where ventilation is already a controlled and fragile system, there is no option that does not carry a cost, no option that does not require resources the colony is already spending elsewhere. Mars lost its magnetic field because it was small. It lost its atmosphere because it lost its field. It lost the ability to protect its surface because it lost its atmosphere. Every layer of hostility the colonists face traces back through that same chain, back to a planet that ran out of interior heat before Earth did, back to a cooling curve that ended the dynamo and opened the sky. The radiation is not a separate problem. It is the final expression of the same original fact. And radiation is not the last of what that fact produces. And underneath all that weight, something has to keep growing. The colony buried under regolith, sealed against radiation, held together against pressure failure, is not a place where survival is passive. It is a place where every basic function of human life has to be actively maintained, continuously, without interruption. Heat, air, water, and food. Food is where the arithmetic gets humbling. A person at rest, in a comfortable office, burns roughly 2,000 to 2,500 calories a day. An astronaut on the International Space Station, under physical demands and the metabolic stress of an unfamiliar environment, burns closer to 2,500 to 3,500. On Mars, where the colony is doing construction, maintenance, EVA work, repairs, and everything else that keeps a fragile habitat functioning, the realistic working assumption is about 3,000 calories per person per day. 100 people, 3,000 calories each. That is 300,000 calories a day. Across a year, that is roughly 110 million calories. Freeze-dried food, the kind designed for long-duration space missions, carries about 450 calories per 100 grams. Dense, efficient. But at that density, feeding 100 people for a year requires roughly 24 metric tons of food. That is the floor. No extra, no waste margin, no agricultural experiment, just survival calories. Now consider what can actually arrive from Earth. A SpaceX Starship, fully loaded for a Mars transit, can carry about 100 metric tons of cargo, fill an entire Starship with nothing but food, and that one mission feeds 100 people for roughly 4 years. That sounds workable, until you remember what else has to fit in that cargo hold. Equipment, spare parts, drilling tools, medical supplies, instruments, building materials, electronics. The mission is not a food delivery. Food competes for every kilogram against every other item the colony requires to stay alive and functional. Realistic early missions carry perhaps 1 to 2 years of food supply. After that, the colony must feed itself. Growing food on Mars is not a future upgrade. It is a founding requirement. And the moment you try to grow food on Mars, a new set of problems opens. Start with sunlight. Mars receives about 43% of the solar energy that reaches Earth's surface. That is not nothing. Some crops can function in that light, but most require more, especially for the caloric yields a colony needs, which means supplemental lighting, which means electricity. Then consider the growing area. A full and varied diet requires roughly 50 to 100 square meters of growing space per person. For 100 people, that is 5,000 to 10,000 square meters. About 1 to 2 acres of active, productive, pressurized growing area. That word, pressurized, is where the engineering problem sharpens considerably. Plants need to breathe. Humans tending those plants need to breathe. A greenhouse on Mars has to maintain something close to Earth's atmospheric pressure on the inside, roughly 100 times what the Martian atmosphere provides outside. The structure is not gently containing slightly elevated pressure. It is holding back near vacuum, continuously, across every square centimeter of its surface. Every panel is like a balloon constantly trying to burst, not slightly stressed, constantly, actively, trying to fail outward. A greenhouse wall can be strengthened, but the panels have to let light through, which means they cannot be buried under regolith. There is no radiation shielding option that also transmits sunlight. The plants get the 43% of available solar energy plus the radiation that travels with it. Plants tolerate radiation far better than animals do, but not without consequence. High enough doses damage DNA, reduce growth rates, decrease yields, and, over enough time, compromise the genetic stability of the seed stock the colony depends on. There is an alternative. Bury the greenhouses entirely. Solve the radiation problem by placing them underground and running the lighting on electricity alone. But something was wrong. Solving the radiation problem by going underground does not reduce the colony's energy demand. It multiplies it. Instead of supplemental lighting to boost 43% solar to a workable level, you now need 100% artificial light for every plant, in every growing bay, every hour of every day. Every solution the colony reaches for turns into an energy problem. And energy is what connects everything. Think about what the colony is already running. Heating systems to hold temperatures above the lethal range. Pressurization systems to maintain an atmosphere the environment will not provide. Water extraction and recycling systems drawing continuously on power. Air processing. Communications. Computers. Medical equipment. Manufacturing. Repair, and construction. Each one of these systems is a continuous electrical load. None of them can be interrupted. None of them have an off switch. So where does the power come from? On Earth, this question has many answers. On Mars, most of them are simply gone. Fossil fuels do not exist on Mars. Coal, oil, and natural gas are biological products. The compressed remains of ancient organisms laid down across hundreds of millions of years of geological and biological history. Mars has no such history. Nothing lived there in sufficient abundance or over sufficient time to produce the carbon deposits Earth sits on. The option does not exist. Wind power fails for a different reason. The force a moving column of air can deliver depends directly on how much mass that air carries, which depends on its density. Mars's atmosphere is about 1% as dense as Earth's. That scaling is nearly direct. A wind blowing at 100 miles per hour on Mars carries roughly the force of a 1 mile per hour breeze on Earth. Not a weaker version of useful, not marginal, essentially nothing. Insufficient to turn a turbine meaningfully. Hydroelectric power requires rivers or waterfalls, moving, liquid water. Mars has none. That leaves two real options. Solar power works on Mars. The panels can generate electricity from the available 43% solar flux. But that cap is already a constraint. And then there is dust. Dust accumulates on solar panels continuously. It reduces output gradually, day by day. Cleaning the panels adds to the EVA workload, which adds to suit wear, which adds to contamination risk inside the habitat. And none of that addresses the larger problem. In 2018, a global dust storm swept across Mars. It lasted months. It reduced sunlight at the surface to levels that could not sustain adequate solar power generation. One rover caught in that storm was the Opportunity rover. It had operated on solar power for nearly 15 years. The 2018 storm ended it. The panels went dark. The rover fell silent and never recovered. A storm of that scale hitting a colony would not just reduce power output, it could reduce it catastrophically at the worst possible moment for an extended period, with no warning sufficient to fully prepare. A colony depending entirely on solar power would need battery reserves capable of carrying it through months of near darkness. Batteries are heavy. They are difficult to manufacture on Mars from local materials. Shipping them from Earth consumes the same cargo capacity that food and equipment are competing for. Nuclear power has none of these vulnerabilities. A reactor generates electricity whether the sun is visible or not, whether a storm has been running for a day or a year, whether it is local noon or the middle of the Martian night. Output is constant, predictable, controllable. The challenges are real. A reactor has to be launched from Earth under full radiation shielding, transported across interplanetary space, landed safely, and set up by a small team of suited workers without a construction depot or heavy equipment nearby. Waste management over the long term requires its own infrastructure, but for a colony that cannot afford a months-long power failure, these challenges are not arguments against nuclear power. They are the price of the only reliable option available. The scale of what the colony needs makes this concrete. A 100-person colony running life support, food production, water systems, manufacturing, communications, and a reasonable growth margin requires at least 1 megawatt of continuous electrical power. 1 megawatt is 1,000 kilowatts running without interruption, day and night, storm and clear, through every failure and every repair. A typical American home draws about 1 kilowatt on average. The colony needs the equivalent of 1,000 homes worth of power, all the time, with no grid to draw backup from and no utility company to call. That is not an engineering footnote. It is the foundation under every other decision the colony makes. The greenhouses need it. The water systems need it. The pressurization needs it. The habitat walls need it. Strip the power, and everything built to keep people alive on Mars begins to fail in sequence, faster than any repair crew can respond. Food and energy looked at the start like two separate problems. They are not separate, they never were. The greenhouses are an energy problem. The water is an energy problem. The air is an energy problem. Every system the colony runs draws from the same continuous power requirement. And that requirement does not go down as the colony grows. It goes up. The ground was toxic. The sky was lethal. The walls had to hold against forces trying to collapse or explode them. And now, the machines that keep everything running need a megawatt of uninterrupted power sourced from options that mostly do not exist. Each layer the colony digs into makes the next one visible, and the layers are not finished. Before any of those systems could run, the crew had to cross the space between the planets. The journey to Mars takes 6 to 9 months one way, depending on trajectory and propulsion. That is not a flight. It is not a voyage in any familiar sense. It is a sustained confinement inside a machine that must function without error for the entire duration, because there is nowhere to stop, nowhere to turn around, and no one close enough to help. The spacecraft carries everything: life support, water recycling, air recycling, temperature control, all of it running without interruption from launch to landing. Critical spare parts travel aboard, because a component that fails with no replacement ends the mission. Food is months of freeze-dried meals, carefully calorie counted, repetitively identical. No fresh produce, no variation. The monotony of it is not a minor complaint. After weeks of the same texture, the same taste, the same packaging opened in the same order, it begins to wear on a person in ways that accumulate quietly, alongside every other psychological pressure the journey applies. Within a few weeks of departure, Earth shrinks behind the spacecraft until it becomes a point of light. Not a disk, not a recognizable shape. A point, brighter than most stars, but indistinguishable from a distance as the weeks pass. Mars ahead is also a point of light. The crew travels between 2 points of light in a darkness that surrounds the spacecraft on all sides. Some people handle this, some do not. Once the spacecraft is underway, the question becomes irrelevant anyway. There is no turning back. Crew dynamics under those conditions become their own engineering challenge. A small group, confined for months with no escape from each other, no privacy worth the name, no reprieve from proximity. Small annoyances magnify. Friction that would dissolve in a normal environment has nowhere to go. Conflict resolution training and clear hierarchy exist precisely because mission planners know the mathematics of confinement. The people inside that spacecraft will need both before they arrive. And arriving is not simple. The landing sequence covers 7 minutes from atmospheric entry to surface contact. 7 minutes during which the spacecraft sheds enormous velocity, survives temperatures that would destroy it without a heat shield, deploys parachutes, fires retro rockets, extends landing legs, and touches down. The crew cannot influence any of it in real time. The sequence is pre-programmed. That is when the pattern broke. Mars sits far enough from Earth that a signal takes anywhere from 4 to 24 minutes to travel between the planets, depending on where both are in their orbits at a given moment. During the 7 minutes of landing, Mission Control on Earth cannot send a command and receive a response. They cannot even watch it happen live. They sit and wait. When they finally receive the signal that entry has begun, the spacecraft has already been on the ground, or failed, for several minutes. Mission Control learns the outcome after the fact. For robotic landers, this has worked. The record of successful Mars landings by uncrewed spacecraft is real and hard-won. But a crewed landing scales the difficulty in every direction. The vehicle is bigger. It is heavier. It requires more fuel to slow, larger parachutes to decelerate, more powerful rockets to cushion the final descent. The margins shrink as the mass increases. And at the end of it, human lives depend on a sequence that no human can interrupt or correct once it begins. That has never been done. Not once. The robotic landing record is good. A crewed Mars landing remains entirely untested. Assume the landing works. The crew steps out of a vehicle that has just performed the most complex automated sequence in the history of human spaceflight. They are physically depleted. 6 to 9 months in a confined spacecraft with resistance bands and a harnessed treadmill, 2 hours of exercise discipline per day to limit what zero gravity and reduced gravity do to muscle and bone is not adequate preparation for immediate hard physical labor. They are not rested. They are not fresh. And they have weeks, not months, to build the systems that will keep them alive. The consumables they arrived with, the oxygen, the water, the food, cover a limited window. Weeks to a few months depending on how the mission is stocked. Within that window, the colony must bring online oxygen production from the Martian atmosphere, water extraction from soil ice, and food growth in pressurized growing areas. The supplies they arrived with are not a comfortable reserve. They are a deadline. Suited work is how most of that early effort gets done. And suited work on Mars is something the Apollo astronauts understood in part and dreaded. The suits are bulky. The gloves are stiff. Pressure builds against every motion, so that reaching, gripping, lifting, and walking all require more force than the same actions on Earth. Suits overheat. A task that takes 10 minutes barehanded, takes an hour in a suit, if it goes smoothly. Apollo astronauts described suited surface work as among the most physically demanding things they had experienced. Mars adds gravity the Moon does not have. Not Earth gravity, but enough that the weight of the suit presses down rather than floating partially away. Imagine digging a trench to bury a cable run in a suit that fights every bend of your arm and every step of your legs, in gravity that is not quite Earth's, but close enough to exhaust you, while monitoring your own oxygen supply and thermal regulation and suit integrity simultaneously. Now, imagine that the trench needs to be finished today, because the power it connects is needed before the oxygen production unit can run. The crew doing that work is small. Every person on a Mars colony represents years of training and an irreplaceable skill set. If a specialist is injured or sick, the colony does not call in a replacement. It calls on whoever has the backup training, which means everyone does. Crew members train for years before departure in their primary roles and in at least one secondary role. A geologist learns enough engineering to substitute in an emergency. A pilot learns enough medicine to assist in a procedure. The redundancy is not inefficiency. It is the minimum viable insurance policy for a group that cannot afford to lose a single functional person during the first years. The physical and psychological cost of those first weeks lands on people who have already spent 6 to 9 months paying a different kind of cost just to get there. What happens inside the colony once they survive the crossing, the landing, and the immediate race against consumables is its own set of problems. And those problems do not get easier as time passes. In some ways, they get harder. The body's struggle on Mars does not end at the airlock. It continues into every decision the colony makes about how to keep itself running. The suits are just the most visible expression of that struggle. Underneath the suits, inside the habitat, the same logic applies. Everything that breaks must be fixed. Everything that runs out must be replaced. Everything that degrades must be compensated for. And on Mars, the margin for failure in all three categories is nearly zero. Manufacturing is where that margin first becomes visible. A 3D printer solves a real problem. If a bracket cracks, you print a new one. If a tool is missing or worn down, you print a replacement. As the colony matures, metal printing expands that capability further. The printer is genuinely useful. The colony genuinely depends on it. But here is what the printer cannot do. It cannot produce a microchip. It cannot fabricate a solar panel. It cannot manufacture a new battery. These are not gaps that better printers will easily close, because they require industrial processes that operate at a scale the colony cannot support. Real manufacturing, the kind that produces complex electronics, requires mining ore, smelting metals, running chemical plants, operating machine shops. All of it requires energy in the tens of megawatts. All of it requires years to build from scratch. The colony does not have tens of megawatts to spare. It does not have years before the first solar panel degrades. So every microchip the colony uses must ship from Earth. Every replacement battery must come in a cargo manifest. Every solar panel lost to degradation or a dust storm draws from a finite stock of spares. The colony can fix anything a 3D printer can fix. For everything else, it waits for the next resupply window. That window is roughly 2 years away. Always. The path to genuine independence, to a Mars colony that needs nothing from Earth to survive, runs through a real industrial base. The estimates for how long that takes are not optimistic. 50 years minimum. More likely a century, possibly longer. In the meantime, the colony is not self-sufficient. It is a workshop that has no harbour traffic, and no way to call for more supplies until the orbital window opens. And what arrives in those windows has to cover everything. Electronics, spare parts, medical equipment. Medical equipment leads somewhere darker. Think about what happens on Earth when someone has a heart attack. An ambulance arrives within minutes. A hospital is reachable within the hour. The hospital has a cardiac team, an imaging suite, a full pharmacy, a blood bank, a surgical theatre. The patient enters a system built over decades specifically to handle that moment. The survival rate reflects it. On Mars, that system does not exist. What exists is a small medical bay, bandages, antibiotics, pain medications, basic diagnostics, an ultrasound unit, a portable X-ray machine, a trained crew member who has some medical background and has not treated a cardiac emergency since training years earlier, no MRI, no extensive pharmacy, no blood bank, no transplant capacity, no specialist who can be called in. Now consider something simpler than a heart attack. Appendicitis. On Earth, appendicitis is routine. A surgeon removes the inflamed appendix in a procedure that takes under an hour. Mortality is below 1%. Patients go home within days. On Mars, appendicitis without a trained surgeon present is potentially fatal within days. The infection spreads. The appendix ruptures. Without surgical intervention and without the right antibiotics at the right dose available in fresh supply, the outcome becomes uncontrollable. A condition that Earth's medical system handles as a minor procedure becomes a threat that the colony may not be able to stop. Skill degradation makes it worse. In a small population, a medical crew member may go years between procedures requiring real surgical skill. The human brain and human hands both lose precision without practice. When the emergency arrives, the skills are not sharp. They are present but rusty in ways that matter enormously when the margin is thin. Telemedicine offers some help. A specialist on Earth can consult, advise, walk through a procedure step by step. But that consultation travels at the speed of light across a minimum of 4 minutes, and as many as 24. In a surgical emergency, real-time guidance is not possible. The crew member is alone with the decision. But here is the part that the medical problem leads to that most people do not anticipate. Medications expire. Every antibiotic in the colony's pharmacy has a shelf life. Potency degrades with age. Pain medications weaken. Drugs that were effective in month 1 are less effective in month 30. The colony's medical capability does not stay constant. It decays. Slowly at first, then faster as expiration dates approach. And manufacturing pharmaceuticals from scratch requires sophisticated chemistry, specialized equipment, and pure reagents that the colony cannot produce. The small-scale synthesis of complex drugs is simply not feasible with colony infrastructure. The only solution is resupply, fresh stocks arriving every 2 years. In the window between them, the colony manages with what it has and hopes what it has remains potent enough. Not slowly degrading, not gradually becoming less reliable, expiring on a fixed calendar that does not respond to need. That is the medical reality. And it leads to a question the colonists will eventually have to answer, one the planners on Earth will have to think through before the mission launches. What happens when someone dies? On Earth, this question has answers so well established that they feel automatic. Burial, cremation, formal ceremony, grief, a grave to visit. On Mars, none of those answers come easily. Burial requires digging into frozen regolith, which is not simple work even with equipment. More than that, a human body is full of Earth microorganisms, trillions of them. Burying an uncontained body in Martian soil introduces those organisms into an environment where planetary scientists have been working for decades to prevent exactly that contamination. Every Mars mission carries protocols to minimize the biological material it deposits on the surface. A buried human body represents a contamination event on a scale that those protocols cannot accommodate. Planetary protection concerns are real, and they do not pause for grief. Cremation is possible in principle, but it costs fuel. Fuel the colony has budgeted for other purposes. It produces gases and residue that have to be captured and managed in a closed environment. It is not forbidden, but it is not free. The third option is the one no one wants to think about, and no one wants to say plainly. In a closed system that is perpetually resource constrained, a human body contains things the colony needs. Water. Organic material that could enrich agricultural soil. The pragmatic calculus is not difficult to perform. It is brutally rational. Reclaim the water content. Compost the organics. Return the matter to the cycle the colony depends on. Whether the people living in that colony could actually do that, whether the psychological weight of it could be carried alongside the daily labor of survival, is a different question entirely. There is no study population. There is no precedent for a small group of humans, years from Earth, making that choice about one of their own. It is the moment where the engineering problem and the human problem become the same problem. And it may be the hardest one the colony faces. The supply chain, the medical bay, the pharmacy shelf, and finally this. Each layer of sustainment on Mars has a ceiling that Earth does not, and none of those ceilings is finished revealing itself. The body does not stop asking questions when someone dies. It keeps asking them in the living. And the next question is not about death at all. It is about birth. Mars' gravity is approximately 38% of Earth's. A person who weighs 150 pounds on Earth weighs roughly 56 pounds on Mars. That sounds at first like a convenience, like freedom of movement, like the sensation of being lighter than you have ever felt. Think about a trampoline. That bounding, effortless sensation of weight giving way beneath you. That is the instinct. That is the wrong one. Human bodies did not evolve on a trampoline. They evolved over millions of years in exactly one gravitational environment. Every bone in the skeleton, every muscle fiber, every chamber of the heart, every fluid system in the inner ear was shaped by 1G. Not shaped by it, incidentally. Shaped by it precisely. Because gravity was the one constant that never changed. The body built itself around that constant the way a tree builds itself around the light. Take that constant away, even partially, and the body begins to dismantle what it no longer needs. The data on this comes from decades of research at the International Space Station, where astronauts live in weightlessness for months at a time. The numbers are not subtle. Bone density drops at roughly 1 to 2% per month in microgravity. The medical term is spaceflight osteoporosis. Over a 6-month mission, an astronaut can lose as much bone mass as a person on Earth loses in a decade of aging. Muscle mass falls by up to 20% on long missions, even with 2 hours of daily exercise. The cardiovascular system deconditions in ways that are difficult to reverse quickly. Returning astronauts frequently cannot stand without fainting. The heart, accustomed to pumping blood in an environment where the fluid distributes evenly, struggles when gravity suddenly pulls everything downward again. Fluid that shifted toward the head during weightlessness, causing the characteristic puffiness and congestion astronauts describe, sometimes leaves lasting effects on the optic nerves. Vision problems have persisted months after return to Earth. All of that comes from 0G, from total weightlessness. Mars' gravity is not 0G, it is 0.38G. And here is where the question becomes one no one can currently answer. We have 2 solid points of reference. We have 1G, which is Earth, and we have decades of human data from living here. We have 0G, which is the space station, and we have decades of human data from living there. We have a brief data point at 16G from the Apollo missions, but those lasted days, not years. What we do not have is any meaningful human data at 0.38G. We have never put a person in that gravitational environment and kept them there long enough to learn what it does. Which means the central question of human health on Mars is genuinely deeply open. Is 0.38 grams enough to prevent the failures that happen at 0G? Or is it only enough to slow them? Those are not the same question. If 0.38 grams prevents the failures, then a Mars colonist who exercises and maintains their health could potentially remain physiologically stable across years of residence. If it only slows them, then the degradation still accumulates, still compounds, still reaches the same destination, just more slowly. We do not know which one is true. Now add the transit. A colonist arriving on Mars has already spent roughly 6 months in 0G aboard the spacecraft. They arrive already depleted, already carrying bone loss, muscle loss, cardiovascular deconditioning. They step into 0.38G in a weakened state and begin whatever partial recovery that gravity allows. Then they stay. Not for a month, not for a year, for years, possibly for the rest of their lives. What happens when they try to come back? The calculation is straightforward and the result is not comfortable. A person fully adapted to 0.38G, with bones and muscles and cardiovascular systems calibrated to that environment, Re-entering 1G would experience something like an Earth person suddenly experiencing 2.6 times Earth's gravity. The bones, already reduced in density, would bear loads they may no longer be able to carry. Fractures become possible not from accidents, but simply from standing. The heart, accustomed to pumping against 0.38 G, may not have the capacity to move blood adequately against full gravity. A colonist who has lived on Mars for 5 or 10 years may find that Earth, the planet they came from, has become physiologically inaccessible. Not difficult to return to, not uncomfortable to return to, impossible to return to. That is the first version of the lock. Adult bodies, over years, adapting to a gravity they cannot unadapt from. Something else was happening. The adult colonists at least arrived on Earth. They spent their first years, their formative years, in 1G. Their bones formed here. Their muscles grew here. Their hearts learned to pump here. Whatever Mars does to them, it is working on a body that was built for Earth. The children will not have that. Fetal development is not simply a genetic process. It is a mechanical one. The growing skeleton responds to gravitational loads. Bones form partly in response to the stress placed on them. The cardiovascular system develops its capacity partly in relation to what the body expects gravity to demand of it. Muscles grow in proportion to the work required. In 0.38 G, those mechanical signals are reduced. Not absent, but reduced. And development is sensitive to the signals it receives. A child born and raised on Mars may grow a skeleton shaped by 38% gravity. Longer, possibly, because the spine is less compressed, but more fragile, carrying less bone mass because less bone mass was ever needed. A musculature built for 0.38 grams. A heart that developed to meet 0.38 grams demands. A body that is, in its most fundamental physical architecture, a Martian body. That body coming to Earth may not be able to stand. Not from illness, not from injury. Simply because the skeleton was never built to carry that weight, the heart was never built to pump against that pull, and the muscles do not have the mass to manage it. The bones may fracture under the weight of the body itself. A child born on Mars may never be able to visit the planet their species evolved on. Think about that for a moment. Not locked out by distance, not locked out by expense, not locked out by politics or resources. Locked out biologically. Locked out because the gravity they were born into shaped them for a world with less of it, and the world of their ancestors now lies permanently beyond the reach of their physiology. This surfaces a question that Earth has never had to ask. Not in the history of medicine, not in the history of ethics, not in any prior framework of human decision-making. If reproduction on Mars means that the children born there may develop abnormally, may be permanently incapable of surviving on Earth, may be biologically confined to one world for the entirety of their lives, is it right to allow it? Who answers that question? The colonists themselves, living under the pressure of building something that must persist? The scientists on Earth, monitoring from a distance of 20 minutes of signal delay? No one? The question is not hypothetical in the distant sense. It is hypothetical only in the sense that no colony exists yet to face it. The moment one does, it becomes the most consequential ethical question the mission carries. More consequential, possibly, than any engineering challenge discussed before it. Because engineering challenges have solutions that can be discovered. This question may not. And the gravity question does not arrive alone. The body has other layers still to reveal. The body is not the only thing Mars holds in place. The mind sits inside the same sealed room, and the room is small. Most of a colonist's waking hours pass inside the habitat. Going outside requires a suit, a checklist, and an acceptance that the environment on the other side of the airlock is hostile in every dimension at once, not one threat at a time, all of them simultaneously. Radiation above, cold pressing in from every surface, pressure trying to drag the atmosphere out of any seal that weakens, dust waiting to coat whatever moves. There is no casual step outside. There is no quick walk to clear your head. There is suiting up, or there is staying in. Think about what that confinement does over weeks, then months, then years. The closest thing Earth has to offer is an Antarctic research station. The people who winter over at those stations are carefully selected, highly trained, and deeply aware of what they are walking into. They still experience stress, depression, and interpersonal conflict that can become serious. They still feel the walls close in as the months pass. Relationships fracture. Sleep degrades. Small irritations compound into something larger. And Antarctica has exits. If a genuine medical crisis emerges, evacuation is possible. If someone falls apart psychologically, they can be pulled out. Most critically, they can call home. Right now. They can hear a voice in real time. They can feel for a moment that the world they left is still reachable. Mars has none of those exits. A message from Earth takes somewhere between 4 and 24 minutes to arrive, depending on where the two planets sit in their orbits. A response takes the same time on the return. A round trip runs anywhere from 8 minutes to 44 minutes or longer. Real-time conversation is not possible. What Mars colonists will have is asynchronous exchange, more like sending letters that arrive days later than like picking up a phone. The warmth drains out of it. The spontaneity disappears. Relationships with Earth do not simply stretch under the distance. They change in character. They become something slower, more deliberate, and ultimately more fragile. Parents, partners, siblings, old friends. The voices grow quieter, not because of any failure of love, but because the medium refuses to carry what a voice actually carries. And there is no help coming. That is the fact the Antarctic analogy cannot hold. Resupply windows open roughly every 2 years, when Earth and Mars align favorably enough to make the journey practical. Between those windows, the colony receives nothing. No equipment, no food, no medicine, no personnel. If something breaks catastrophically, the colony fixes it with what it has. If someone's medical situation exceeds the colony's capacity, the colony manages it with what it has. If a crisis exceeds the crew's combined ability to respond, the colony absorbs the outcome. There is no rescue mission. A rescue mission would take months to launch and 6 to 9 months to arrive. By the time it reached Mars, the crisis would have resolved one way or another, long before any help touched down. This is what the Mars mental health problem actually is. Not the stress of hard work, not the tedium of routine, the deep, structural knowledge that there is no flaw beneath you, that the safety net Earth provides to every human being alive, the certainty that help is theoretically reachable, simply does not exist on Mars. The crew knows it. Every hour of every day, they know it. A small group of people, confined together, unable to separate, aware that the next contact with the broader human world is measured in years rather than days. The crew dynamics research on analogous environments, submarines, long-duration spaceflight simulations, Antarctic winter stations, all point in the same direction. Conflict emerges. It is not a failure of professionalism or character. It is a predictable consequence of confinement without exit. On Earth, when a relationship becomes unbearable, a person leaves. They create distance. They give themselves time. On Mars, the crew member who made you furious at breakfast is at the table again for dinner, and will be tomorrow, and for every meal for the next 18 months, until the window opens and a cargo ship might arrive without anyone on it who can help. Mental illness under these conditions is not an edge case to plan around. It is an expected outcome to plan for, and the planning is severely limited. Psychiatric care on Mars consists of whatever training the crew carried, whatever medications were stocked before departure, and a remote consultation with Earth professionals who respond 12 minutes later per message, with advice shaped by information that is already 12 minutes old. There is no evacuation. A colonist in a serious psychiatric crisis remains in the habitat, with the crew in the small room, managing. Then the data shifted. Over time, something else begins to happen that is not entirely about crisis or suffering. The colonists start to become something different. Language drifts first, slang emerges, words for things that only exist on Mars, for equipment configurations, for atmospheric readings, for the particular quality of light through a dusty panel. Shared references accumulate that mean nothing to someone on Earth. Rituals form, small ones at first, then larger ones. A way of marking the end of a Martian year, a tradition around the first successful harvest, an identity tentatively, that is not Earth person stationed on Mars, but something else, something without an established name. Anthropologists who study isolated communities would recognize the shape of it. Shared adversity accelerates group cohesion. Shared vocabulary creates insider culture. Over enough time and enough generations, a genuinely distinct people can emerge from conditions like these. That is anthropologically interesting. It is also, politically and emotionally, one of the most consequential unknowns the mission carries. A Mars colony that begins to think of itself as Martian rather than as an extension of Earth is a colony that may eventually resist Earth's authority, Earth's priorities, Earth's framing of what the mission is for. Whether that divergence is healthy, dangerous, or simply inevitable is a question no one has answered. Long-term psychological sustainability of a permanent human community on Mars is genuinely unknown. We have no study population, we have no precedent. We have isolation analogues that all fall short. And then the sky closes. Earth has dust storms. The Sahara throws walls of dust that swallow cities for hours. The American Southwest gets storms that turn the horizon brown and ground aircraft across 3 states. They are serious. They are temporary. They are localized, and they end. In 2018, a global dust storm covered Mars for months, not a region, the planet. A storm that spread until it swallowed the entire surface, pole to pole, and sat there for months. Opportunity was a rover that had been operating on the Martian surface for nearly 15 years. It was built for a 90-day mission. It had survived everything Mars threw at it for more than 14 years, beyond that design lifetime. Then, the 2018 storm came. Opportunity's solar panels could no longer generate enough electricity to keep the rover alive. Engineers on Earth sent signal after signal. They waited. The rover never responded again. Not because it was destroyed by wind or cold alone, because the dust was so thick, for so long, that the panels could not recover. The clock inside may have failed. The cold during the powerless months may have been too deep. The panels may have been too coated to ever receive enough light again. We don't know exactly which factor ended it. We know it ended there, in the dark, in the longest storm it had ever seen. For a human colony, a months-long global dust storm is not weather. It is a multi-system crisis arriving simultaneously. Solar output during a major storm can drop to 10 or 20% of normal, or lower. A colony running on solar power does not simply dim its lights. It begins rationing every system that draws current. Greenhouses, heating, water recycling, air processing, communications. Not enough heating means the habitats grow cold, slowly at first, then dangerously. Slowed air recycling means carbon dioxide concentrations begin to rise. Carbon dioxide, the gas that makes up 95% of the Martian atmosphere outside the walls, is the gas that will kill the crew inside if the recyclers fall behind. Halted water recycling means drawing on reserves, which are not infinite. Even a colony with nuclear baseline power faces hard choices about what to run and what to suspend. And the dust does not stay outside. Every time a crew member returns from an EVA, the airlock carries dust inward. Over days, this is manageable. Over months, it accumulates. The interior surfaces acquire a thin coating of Martian regolith. The air filtration systems run constantly and hard. Filters require replacement. Replacement filters are not manufactured on Mars. They were packed before departure, counted before departure, rationed from the beginning. Running out of filtration capacity during a months-long storm is not a minor inconvenience. The colonists have been breathing low-level Martian dust since the storm began. Martian dust contains perchlorates. Chronic perchlorate inhalation disrupts thyroid function and may damage lung tissue over time. The storm turns a known chronic risk into an acute one. Equipment wears faster in every direction. Rovers accumulate dust in their joints and wheel mechanisms. Airlock seals degrade. Solar panels that are scratched by abrasive particles lose efficiency permanently. They do not recover when the storm ends. Each storm leaves the equipment slightly worse than it found it. Cumulative storms shorten the operational life of every system the colony depends on. Visibility outside drops to an oppressive brown haze. Mars has no GPS network. Navigation during surface operations relies on dead reckoning, on knowing where you started and how far you have traveled and in which direction. In a dust storm, that calculation becomes dangerous. A rover that miscalculates position in low visibility might drive into a crater that was plainly visible the day before the storm began. And above all of this, through all of it, the crew sits in the small room, the sky brown outside every viewport. No sun visible, no horizon. No change in the quality of light from morning to evening. Weeks of it, then months. Researchers who study seasonal affective disorder, the depression that arrives with shortened winter days and reduced sunlight, describe what extended light deprivation does to mood, cognition, and motivation. Now imagine that effect, not over a winter, but over a planet-wide storm that has no scheduled end date. The brown does not lift on a calendar. This is the convergence point. Every constraint the colony carries, power, air, water, physical health, mental health, equipment, becomes stressed at once. The storm is not a weather event. It is the moment when all the separate threads of Mars's hostility pull taut at the same time. And storms like the 2018 event are not anomalies. They are part of the Martian cycle. The colony that survives one will eventually face another. And that is not the last thing the planet holds in reserve. Step back from the planet for a moment. Step back from the dust and the dead sky and the brown light through the viewport. The storms will come again. We know that now. But before the next one arrives, before we count the cost of surviving it, there is a quieter question sitting underneath everything this planet has shown us. Why send humans here at all? That question has an easy answer and a harder one. The easy answer is that people have always gone to hostile places and survived. Antarctica, the Sahara, the deep ocean. If we can endure those, the argument goes, we can endure Mars. It sounds reasonable. It has a certain logic to it. But the picture did not hold. That logic dissolves the moment you hold the places side by side. Think about Antarctica. Winter temperatures fall to around minus 30 degrees Fahrenheit. The isolation is real. The cold is serious. People have died there. But outside every research station door, the air is breathable. If a heating system fails, a researcher can dress in every layer they own and survive until rescue arrives. Medical evacuation by plane takes hours to days. The wildlife, seals and penguins and fish, is not farmable on a large scale, but it exists. Life is present. Rescue is possible. Exits are open. Think about the Sahara. The heat is real. The dehydration is dangerous. But the air outside is breathable. Water exists if you know where to look. Insects, reptiles, plants around you. A person with skill and some luck can survive long enough for help to come. The Sahara is trying to dehydrate you. It is not trying to asphyxiate you. Think about the deep ocean. Crushing pressure, total darkness, extreme cold. Humans visit in submersibles, not on foot. But those submersibles can surface. The crew can return to the ship. The ocean floor is teeming with life even at its most extreme depths. Mars offers none of these. No breathable air. No native life to hunt or eat or even observe with hope. No surfacing to safety. No rescue from Earth at any timeline a stranded person would survive to see. Step outside without a suit, and the atmosphere kills you in minutes. Not from the cold alone, not from dehydration alone. The pressure and the chemistry together. There is no improvisation that saves you. There is no fallback that buys you time. The technology argument tries to answer this. Suits and habitats provide protection, the argument says. They replace what the environment refuses to offer. And that is true as far as it goes. But technology fails. Seals crack, electronics malfunction, power systems fail at the worst possible moment. On Earth, when technology fails in a hostile place, there is a natural fallback underneath it. Air is still there, water can still be found. Temperatures that are brutal are not instantly lethal. The fallback is built into the planet. On Mars, there is no planet underneath the technology. There is only more hostility. The technology is not supplementing survival. It is survival. Remove it. and nothing natural steps in to buy time. The International Space Station is the closest existing comparison for sustained human life in an engineered environment. When something goes wrong on the ISS, the crew can evacuate via Soyuz capsule and be back on Earth's surface within hours. Hours. A Mars crew has no such option. Committed to the next launch window, which opens roughly every 2 years. Not hours, not days. 2 years at best, of waiting for a rescue that would then take 6 to 9 more months to arrive. That is not a difference in degree. Not harder, not more extreme, not a longer wait. Qualitatively different. The ISS analogy holds right up until it collapses, and it collapses on evacuation. The comparison between Mars and Earth's frontier places holds right up until it collapses, and it collapses on air and exit. Success in Antarctica does not generalize to Mars. The experience is not transferable. The lesson is not applicable. Which brings us to the economic question, and here the picture does not improve. Serious analyses of what a genuinely self-sustaining Mars colony would cost put the figure somewhere between hundreds of billions and trillions of dollars. Even a colony of a few hundred people, capable of sustaining itself without constant resupply, requires infrastructure on a scale that has no precedent in human exploration history. Initial crewed missions run into the tens of billions each. Individual launches, even with reusable rockets like Starship, cost hundreds of millions per flight, and many launches are required. Cargo pre-positioned before crew arrives. Crew flights themselves. Resupply missions arriving every 2 years to cover what the colony cannot yet produce locally. And what returns on that investment? Nothing that can be shipped back. Nothing on Mars is valuable enough to justify the cost of lifting it off the surface and returning it to Earth. If you mined gold on Mars, the cost of bringing it home would exceed the value of the gold. There is no resource play here. There is no economic model in which Mars becomes profitable. This makes Mars unlike every historical colonial expansion on Earth. When European settlers crossed the Atlantic, the colonies they established could eventually grow their own food, trade their own goods, develop their own economies. They became economically independent. They could sustain themselves. Some became wealthy. Some became nations. A Mars colony cannot follow that path. Not for decades. Not for most of a century. Not until a level of industrial and agricultural capacity is built that currently exists nowhere off Earth. Until then, the colony depends entirely on funders, governments, corporations, philanthropists, whoever is willing to continue writing the checks. And if those funders change their priorities, suffer a financial crisis, lose public support, or simply grow tired of subsidizing a distant outpost that cannot sustain itself, the colony faces an existential crisis it cannot resolve from the inside. The people are already there. They cannot simply leave. They wait for the next launch window. They count their supplies. They hope the funding holds. Now consider the 4 arguments most commonly made in favor of colonization. They are worth examining carefully because each one carries real weight, and each one, under scrutiny, is weaker than it first appears. The first is science. Mars colonists would conduct research that robots cannot. They would adapt to unexpected findings in real time, dig where a rover cannot dig, make the kind of intuitive leaps only a human mind on the ground produces. This is true. Humans are more flexible than machines in ways that matter scientifically. But robots have reached Mars. Rovers have driven across its surface for years. Landers have measured its chemistry. Sample return missions are in development. The science case for humans, real as it is not the science case for colonization. A research outpost is not a permanent settlement, and the cost difference between sending scientists for temporary missions and building a self-sustaining colony is enormous. The second argument is technology spin-off. The Apollo program generated advances in computing, telecommunications, and materials science that reshaped civilian life. Mars colonization would do the same. This is almost certainly true, but it is an argument for investment in those fields directly, not for routing that investment through the most expensive and dangerous possible pathway. Funding fusion research directly reaches fusion faster than funding Mars, in hopes fusion emerges as a byproduct. The third argument is inspiration. Apollo inspired a generation. Mars would inspire another. Children who watched the first humans land on Mars will become scientists and engineers and explorers who carry that vision forward for decades. This is also true, but inspiration is not a universal experience. Others find it in medicine, in environmental protection, in art, in justice. What inspires one person leaves another unmoved. Whether Mars colonization is the best use of resources for generating inspiration is not a factual question. It is a values question. And values questions cannot be answered by pointing at the Apollo precedent. The fourth argument is the backup planet. Earth faces real existential risks. Asteroids, nuclear war, pandemic, climate change. A second home for humanity hedges against catastrophe. This argument feels compelling. It has genuine emotional force, but the answer was stranger than expected. Even a badly damaged Earth after a nuclear exchange, after a major asteroid impact, after severe climate disruption, remains more habitable than Mars under any realistic scenario. The air would still be breathable, water would still exist, temperatures, even at their worst, would not require continuous life support technology just to step outside. A colony on a dying Earth would be better positioned than a colony on Mars that never had what Earth is losing. And the backup planet argument rests on an assumption that does not hold. It assumes the Mars colony would be independent enough to survive an Earth catastrophe. But we have just spent this entire conversation establishing that a Mars colony, for decades, possibly for a century, cannot survive without continuous resupply from Earth. The moment Earth suffers a catastrophe severe enough to threaten human civilization, the supply chain to Mars breaks, and the colony dies. The same resources spent building resilience on Earth, asteroid defense systems, pandemic preparedness, nuclear arms reduction, climate response, would protect far more people far more reliably than a colony of a few hundred people on a planet that cannot sustain itself. What remains after each of those four arguments has been examined is something older and harder to argue against. Humanity should expand because expanding is what we do. Because the reach toward new horizons is part of what it means to be human. Because staying is not an option we were built for. That argument is not wrong. It is just not enough to close the conversation. And it is not the last word on what Mars really tells us. But the philosophical case does not arrive alone. It carries obligations, and those obligations are not small. The first one concerns what might already be on Mars. We do not know whether Mars is lifeless, we suspect it is, but the suspicion is not certainty. Liquid water existed on Mars for hundreds of millions of years. Microbial life on Earth began in water, in heat, in chemistry that Mars once had. If life ever started there, it may not have ended. Some microbes on Earth survive in conditions that would kill almost anything else. Extreme cold, extreme radiation, near total desiccation. Mars has pockets of subsurface warmth, traces of liquid brines deep underground, environments where the chemistry is at least conceivably hospitable. We don't know if anything lives in those pockets, but we haven't ruled it out. And here is where it gets strange. The very act of sending humans to look for life on Mars may destroy what we hope to find. Every human being carries roughly 37 trillion cells, and surrounding and inhabiting those cells are somewhere between 10 and 100 trillion microbial organisms. Bacteria, archaea, fungi. A human is not a single living thing. A human is an ecosystem. We cannot sterilize ourselves. We cannot leave our microbiome behind. The moment a crewed spacecraft opens its hatch on Mars, Earth life begins entering the Martian environment. Some of those organisms may die quickly, others are built for extremes. Some may find the Martian subsurface hospitable. Earth life may outcompete, displace, or hybridize with whatever Martian life is there. We may contaminate the very sample we traveled billions of miles to study. The search for Martian life could make finding it impossible. Not difficult, impossible. Robotic missions are not sterile either, but they carry far fewer organisms, and the organisms they do carry are passive rather than metabolically active and constantly shedding. The planetary protection protocols for unmanned landers are strict for exactly this reason. For crewed missions, the challenge scales by orders of magnitude. We don't fully understand how to solve it. We don't even fully agree on whether the risk justifies stopping. That disagreement runs deep. Some scientists and ethicists argue that Mars, if it harbors even microbial life, deserves protection. That we have no right to colonize a world that is already, in some sense, inhabited. Others argue that Mars is almost certainly lifeless, that treating a barren rock as a nature preserve is a failure of pragmatism, and that the science is best done by humans in person. No consensus exists. The question is not a technical one. It is a values question. What do we owe a world we did not create, and which may not be able to resist us? The equity question is just as uncomfortable. Early Mars missions will not carry everyone. They will carry the most qualified candidates, the healthiest, the most technically skilled, the most psychologically resilient. People selected through years of rigorous screening from populations that already had access to the education, resources, and opportunities that made them candidates. Mars exploration begins as an elite endeavor. That is not a failure of planning. It is a structural reality of what crewed deep space missions require. But it means that decisions about the future of humanity, if Mars colonization proceeds at civilizational scale, will be made first by a very narrow slice of humanity. The shape of a multi-planetary species will be sketched by those who were already advantaged on the planet they came from. That framing is uncomfortable to sit with. It is not a reason to stop, but it is a reason to notice. And then there is the question of what happens once people are actually living on Mars and someone has to make rules. The 1967 Outer Space Treaty established the foundational legal framework for human activity beyond Earth. Under that treaty, no nation may claim sovereignty over any celestial body. The Moon, Mars, asteroids, none can be owned. They are, in the treaty's language, the province of all mankind. That language sounded generous in 1967, when spaceflight was a competition between two superpowers and colonization was barely science fiction. It sounds more complicated now. The treaty says no nation can claim sovereignty, but it does not clearly prohibit companies from claiming the resources they extract. If a corporation mines Martian rock, or a private colony builds infrastructure, the legal status of what they possess is genuinely unresolved. Patterns that look familiar from Earth's history, the accumulation of resource rights without formal sovereignty, the practical reality of possession regardless of legal theory, are precisely what the treaty's language leaves open. But here is the governance problem that no treaty can solve on its own. A message from Mars takes between 4 and 24 minutes to reach Earth, depending on where the planets are in their orbits. A round-trip conversation, a question and its answer, takes between 8 and 48 minutes minimum. Earth-based governance of a Mars colony in real time is physically impossible. Every decision made on Mars will be made by people on Mars because the physics of the distance demands it. Over time, over years, over generations, a colony that must govern itself by necessity may begin to see itself as governing itself by right. Legal questions about authority will drift toward practical questions about identity. What started as a jurisdiction problem becomes a political one, and no one has written the rules for that yet. The reasonable path, given all of this, is not abandonment. It is patience. Robotic exploration can continue without contamination risk at planetary scale. Rovers, landers, aerial drones, sample return missions, all of these extend our knowledge without sending a human microbiome to the Martian subsurface. Technology can be developed gradually. Habitat design, closed-loop life support, radiation shielding, food production, medical systems, these can be tested and improved over decades, on Earth and in orbit, before they are asked to function as the only barrier between people and death. The decision to send humans permanently to Mars should arrive when the technology is actually ready. Not because a billionaire has a timeline, not because of nationalist competition, not because the inspiration value is high this decade, because the people who go deserve systems that are actually prepared to keep them alive. And now, sitting with the full weight of what this conversation has covered, the challenges deserve one last accounting. Not to rehearse the despair, to let the honest picture land quietly. The The radiation is continuous and cumulative. The cold is extreme and unforgiving. The atmosphere is nearly absent and actively poisonous. The pressure wants to kill you the moment the habitat fails. There is no water cycle, no food chain, no accessible food source. The soil is laced with a chemical that disrupts human metabolism. The gravity is too weak for the body built to survive in it, and no one knows exactly what too weak for too long produces in adults or in children born there. The psychology of permanent, inescapable confinement has no precedent at this duration. The medical system is a shadow of what any serious emergency requires. The manufacturing base for self-sufficiency is a century away at minimum. The supply line to Earth is a 2-year gap between lifelines, and if that line breaks, the people on the other end of it are already gone. Some of these constraints may yield to future technology, radiation-resistant genetic engineering, artificial gravity from rotating habitats, fusion power, advanced robotics. Each of these could change the arithmetic. We don't have them yet. We don't know when we will. We don't know if some of the physiological problems are solvable within biology as it currently exists. Short-term human missions will probably happen. The engineering is almost there. The will is clearly there. Someone will stand on Mars within this century. That is not the question. The question is whether large, thriving, genuinely independent Mars colonies are coming. And the honest answer is, not soon. Not without technologies that don't yet exist. Possibly not for a very long time. And if people go before those technologies exist, some of them will not come home. Not as a dramatic exception. As an expected outcome. The environment will be trying to kill them every moment they are there. Some moments it will succeed. That is not a failure of courage. It is a statement about Mars. What all of this finally asks of us is not despair and not surrender. It is clarity. The deepest value of looking at Mars this carefully, of tracing every layer of hostility down to its roots, may not be a plan for colonization. It may be a new way of seeing the planet we are already on. Every breath of air you take, the air is just there, available, not requiring machinery. Every sip of water costs nothing in atmospheric pressure or perchlorate filtration or energy budgets. Every time you step outside without a suit, without checking seals, without calculating oxygen remaining, you are doing something no Mars colonist will ever do. The unprotected sunrise, the unfiltered sky, the ground that does not poison what you plant in it. These things feel ordinary because they are ordinary here. They would be unimaginable there. Earth is imperfect. Earth has problems that demand urgent attention. But it is worth noticing that Earth is not a problem we are trying to survive. Earth is where survival was already solved, billions of years ago, by chemistry and time and the right distance from a star. Mars is where survival must be engineered from scratch at enormous cost, against every environmental force, with no margin for failure. Earth is easier to save than Mars is to colonize. That is not a small thing to notice.